Hi, Assalamualaikum and a very good morning. So now we're going to do chapter 6, chemical equilibrium, and we're going to focus on the subtopic of 6.2 equilibrium constant, part 3 of the video. So in this video, we're going to learn on how to calculate the value of Kc, Kp, as well as the quantities of species present at equilibrium. So for the learning outcome of D, we're going to look about that in this video, which is in part 3. For the learning outcome of E and F, we're going to look about that in the next video, which is in part 4. So without any further ado, let us start with part 3 of the video first. So, solving equilibrium problem. So in order to solve the equilibrium problem, we're going to use the ice table. So the ice table is basically representing initial, change, as well as the equilibrium. And that is where the name of ice is being obtained. And the ice table can be written in terms of the concentration, which is in molarity, or we can adjust that according to our situation. For example, we can use it for ATM, ATM, or ATM. Or we can also put it in terms of mole. So it is adjusted according to our needs. And in order to use the ice table, we need to write back the equation which is in equilibrium, and we're going to use it in order to solve the problem that we need. So we need to express the equilibrium concentration for all the species in terms of the initial concentration, which is in these boxes here. And then we're going to use a single unknown, which is, we're going to put it as X, which represent the change in the concentration. Okay. So the reactant will be decreasing by time, and the product will be increased by time. And it is depending on the stoichiometry. So if it has a stoichiometry of 1, then it will increase by 1x. If they have a stoichiometry of 2, then it will increase by 2x. Okay? And then we need to write the equilibrium constant expression in terms of the equilibrium concentration in order for us to solve the value of Kc. Okay? And in order to get the value of x, if the Kc is being given, the value there, we can use the Kc expression as well as the value in order to work out the value of x. Okay? And we're going to solve the value of x, and from here we can obtain back the equilibrium concentration. So it is quite difficult to understand it by words, and to understand more about that, let us look into the various examples in order to support our learning for ice table. So for example number 1, a mixture of the hydrogen gas, iodine, was prepared by placing 0.2 mole of hydrogen gas as well as 0.2 mole of iodine gas in a 2-liter flask at a certain temperature. After a period of time, the equilibrium was established. Okay? And at equilibrium, the concentration of the iodine will drop to 0.02 molar. And then we need to determine the value of Kc for this reaction at this temperature. So at initial stage, because it was prepared, so we know that we have 0.2 mole of hydrogen gas, 0.2 mole of iodine, and this was placed inside a 2-liter flask. And then we need to find the value of Kc. Okay. So in order to solve this question systematically, we can use the ice table. So we need to write the equation again, which is the hydrogen gas reacting with iodine gas in order to produce 2 mole of hydrogen iodide. So the equation here is already balanced. So we have the initial change as well as the equilibrium, and then it is denoted in terms of the concentration because we need to find the Kc. Okay, and as what you know that since we are denoting it in terms of concentration and we have the number of mole here, so we know that our concentration is basically equal to the number of mole divided by the volume. So the volume is given as 2 liter. So at initial, which is at initial stage, we have 0.2 mole of the hydrogen gas. So we can find the concentration by dividing the number of mole with the volume. So we're going to get the initial concentration of the hydrogen gas to be 0.1 molar. Similar thing for iodine. So number of mole divided by volume, we're going to get 0.1 molar. And at the initial stage, there is no hydrogen iodide that it's going to form. So pada mulanya, produk langsung tiada. So we're going to put it as 0. Okay. But as time goes by, there's going to be a decrease in the amount of the reactant because the reactant is started to produce the product. So the reactant will reduce by a certain amount, which is an unknown amount of X. So we're going to put it as minus X because it is the reactant. Similarly to the iodine, which is minus X. Okay. And for the product here, because the reactant has started to convert into the product will started to increase by a certain amount of 2x. Why 2? Because it has a stoichiometry of 2 here. Okay. And at equilibrium, the initial plus the change here, you're going to get 0.1 minus x. Similarly to iodine, which is 0.1 minus x. And then for the hydrogen iodide, we're going to have 2x at plus. Okay. And from the question here, it was stated that at equilibrium, the concentration of iodine at equilibrium is 0.02 molar. Okay, so you know that this thing here is equal to 0.02. So you will get the idea here that you can find the value of x. So 0.1 minus x is equal to 0.02. So once you do the maths, you're going to get the value of x to be 0.08. So the x value here, you can substitute it back into this equation. So for the concentration of the hydrogen gas, 0.1 minus the value of x, 0.08, you're going to get 0.02 molar. Similarly for the hydrogen iodide, so 2 times 0.08. So lastly, we're going to get the concentration of Hi to be 0.160 molar. So now we have obtained the concentration of the hydrogen gas, iodine, as well as the hydrogen iodide at equilibrium. Okay, but the question asks us to find the Kc. So in order to do that, we need to write the Kc expression first. So for our Kc, it's going to be the ratio for the concentration of the product, which is Hi to the power of 2, because the stoichiometry here is 2, divided by the concentration of the reactant, so hydrogen gas, as well as the iodine gas. So the value of Hi is already obtained here, which is 0.16 to the power of 2. Okay, do not forget the power here. And then for the hydrogen gas, we have 0.02. And then for the iodine, we have 0.02. So once we do the math and plug in the value, we're going to get the value of Kc to be 64.0 without any unit. Alright, so this is how we answer question number 1. Now we're going to look into the next question, which is example number 2. So for the atmospheric oxidation for the nitric oxide was studied at 184 degrees Celsius with the pressure of 1 atm of NO as well as 1 atm of oxygen. At equilibrium, the partial pressure of oxygen is 0.506. We need to calculate the Kp. Okay, so initially we are given 1 atm of NO as well as the initial partial pressure of oxygen. So we need to use the ice table in order to obtain each species at equilibrium, and then we need to calculate the Kp similar as before. So we're going to do the ice table, and then we need to write back the equation. So our equation here is balanced, so they are fine. So at initial, we have the partial pressure of the NO to be 1 atm. Okay, and then we also have 1 atm for the oxygen. And then at initial stage, the concentration of the product, which is the nitric dioxide here, is 0. And then as time goes by, the reactant will be reduced by 2x because we have the stoichiometry of 2 here. And then for the oxygen, it's going to reduce by x. And then for the product, by time, it will increase by the amount of 2x because it has a stoichiometry of 2. And for the partial pressure at equilibrium, we're going to add up together, which is 1 minus x. And then it's going to have 1 minus x for the oxygen. And for the nitrogen dioxide, we're going to have the final value at equilibrium going to be 2x. And it was stated that at equilibrium, the partial pressure of oxygen is 0.506 atm. So we know that this equation here is equal to 0.506 atm. Okay, so from the start here. And we can find the value of x. So once we do the math, we're going to get the value of x to be 0.494. Since we have known the value of x, we can substitute it back into the following expression here. So for the nitric oxide, we have our 1 atm minus 2 multiplied by 0.494, which is our x value. And then when we do the maths, we're going to get the partial pressure of the NO to be 0.012 atm because we are talking about pressure. Okay. And then for the nitric dioxide, we have 2x. So 2 times 0.494, we're going to get the answer going to be 0.988 atm. Okay, so we have find the partial pressure of each species at equilibrium. Now we need to find Kp. Okay, so we need to write the Kp expression first. So Kp is equal to the partial pressure of the product, which is PnO2 to the power of 2 because of the stoichiometry, divided by the partial pressure for the reactant, which is NO to the power of 2, as well as the partial pressure of oxygen to the power of 1. And this refers to the partial pressure at equilibrium, okay, in which we have obtained that. So we're going to plug in the value. So PnO2, which is 0.988 to the power of 2, divided by PnO, which is 0.012 to the power of 2. So do not forget the power here. And then the oxygen, which is 0.506. So once we do the maths, we're going to get the Kp value to be 1.34 times 10 to the power of 4 without any unit because Kp is treated to be dimensionless. Okay, so it has no unit. All right. Now we're going to move on to the example number 3. So phosgene COCl2 will be decomposed by the following reaction. So COCl2 will be decomposed in order to produce carbon monoxide as well as the molecular chlorine, which is Cl2. And then the Kc here is given to be 8.3 times 10 to the power of negative 4 at 360 degrees Celsius. So we need to determine the concentration of COCl2 as well as COCl2 when the 5 mole of phosgene decomposes and reaches the equilibrium in a 10-liter flask. So we need to find the concentration of this species at equilibrium. So when we need to find the concentration at equilibrium, as usual, we need to do the ice table. So we need to write the equation, which is COCl2, decomposes into CO as well as the molecular chlorine. And we are talking about the concentration, and therefore we need to put it in terms of molarity. And the info that we have is we have the 5 mole of phosgene. So phosgene here refer to COCl2. So as usual, in order for us to find the concentration, we need to divide the number of mole with the volume of the flask. So we have 5 mole, we need to divide it with 10 liter. So 5 divided by 10, we're going to get the concentration to be 0.5. So at initial stage, we only have the concentration of the reactant. And for the product here, we're going to put it as 0 as well as 0. Now, as time goes by, the concentration of the reactant will reduce by x. Meanwhile, the concentration of the product will increase by plus x and plus x respectively. So at equilibrium, we're going to have the concentration of the phosgene to be 0.5 minus x. For the CO and Cl, we're going to have x and x respectively. Okay, and from here, you know that you have the value of Kc. Therefore, you can write your Kc expression first. So Kc is equal to the concentration of the product, which is CO to the power of 1, as well as Cl to the power of 1, divided by the concentration of the reactant, which is COCl2. And then you can substitute your CO here, which is at equilibrium equal to x, your Cl2, which is equal to x, and then your COCl2 to be 0.5 minus x. And then you also know that your Kc is equal to 8.3 times 10 to the power of negative 4. Okay, so from now you can find the value of x. Okay, kita boleh cari value of x. How can we do that? So we need to, so we can get x squared here divided by 0.5 minus x, and then we're going to bring this denominator here to the right hand side. Okay, so you're going to get x squared is equal to 4.15 times 10 to the power of negative 4 minus 8.3 times 10 to the power of negative 4x. So we're going to bring this term back on the left hand side in order to make a quadratic equation. So we're going to continue that on the next slide. So this is the last writing on the previous slide, and then as I mentioned, we're going to put it in terms of the quadratic equation, which is ax squared plus bx plus c is equal to 0. So we're going to put it as a subject on the one side, which is on the left hand side. So as what you can see here, we're going to have the quadratic equation. So you're going to plug in the value inside your calculator and then solve for the quadratic equation. So you're going to have two possible answers. So for the possible answer number 1, you're going to have negative 2.0 times 10 to the power of negative 2. And then another possible answer is you can get the value of x to be positive 2.0 times 10 to the power of negative 2. So which value should you choose? So essentially, we need to choose the more positive value. Okay, because concentration cannot be negative. Okay, because if you were to plug the value of negative 2 times 10 to the power of negative 2, it is impossible or illogical to have concentration which is negative. We can never get a negative concentration, and for that reason we just gonna ignore this one, and then we're gonna take this value for our x. Okay, so from here, since we have the value of x, we can now determine the concentration of CO, Cl2 as well as the phosgene at equilibrium. So we're going to substitute the value of x into this expression here. So for the CO, it is basically equal to x, where x equal to 2.0 times 10 to the power of negative 2 molar. Similarly, for the molecular chlorine, which is the Cl2, it will be equal to x, which is 2.0 times 10 to the power of negative 2 molar. And meanwhile, for the concentration of phosgene, it's going to be 0.5 minus x, which is, we're going to do the maths, we're going to get 0.48 molar. Okay, and this is how we find the value of x step by step in order to determine the concentration at equilibrium when the Kc is being given. All right, so now we're going to look into the last example, which is example number 4. So at 1280 degrees Celsius, the equilibrium constant Kc for the reaction is given to be like this. So we have the bromine gas dissociated in order to form two bromine gases atom, and the Kc is given to be 1.1 times 10 to the power of negative 3. So here is the Kc. So if the initial concentration of the bromine gas to be 0.063 molar and the bromine atom to be 0.012 molar, we need to determine the concentration of this species at equilibrium. So nak cari concentration at equilibrium. And as usual, we need to do the ice table. So we're going to construct that. So Br2 gas produces 2 mole of the bromine gases atom. So the equation is already balanced. And at initial stage, the concentration here going to be 0.063. Meanwhile, for the Br atom, we're going to have 0.012. And as time goes by, the concentration of the reactant will reduce by minus x, and the concentration of the product will increase by 2x because of the stoichiometry here. Okay, and at equilibrium, we're going to have 0.063 minus x, and then for the bromine atom, we're going to have 0.012 plus 2x. Okay, and from here, you can write your Kc expression. So your Kc is basically the Br concentration to the power of 2 divided by the bromine molecule. Okay, and then you can substitute your BR, which is at equilibrium, which is 0.012 plus 2x to the power of 2 divided by the bromine molecule, which is 0.063 minus x. And then this Kc here will refer to 1.1 times 10 to the power of negative 3. So you're going to do a cross multiplication. So you're going to bring this to the right hand side. Okay, so you're going to expand this 0.012 plus 2x squared. When you expand that, you're going to get this value. Okay, and then when you bring this to the left, to the right hand side, you're going to get this term here. And as usual, you're going to write it on the one side only, in which we're going to produce a quadratic equation. Okay, so all this term here will be bring into the left hand side. So finally, we're gonna get the value gonna be 4x squared plus 0.0491x plus 0.0000747 equal to 0. So you're gonna plug in the quadratic equation into your calculator in order to solve it, and then you're going to get two possible value of x. So you're going to get x to be negative 0.0105, and then you're going to get the x value to be negative 0.00178. So we have both negative on for our possible value of x. But which value should we choose? So for this reason, we need to choose the value that is more positive. So we need to choose this one because this one is more closer to 0. Okay, so let's say this one is 0, right? So we have negative 0.00178, and then we have negative 0.0105. So this value here is closer to 0 and it is more positive in comparison to this one. Okay, so we're gonna choose this value. Okay, so we can put the x value in order to solve the concentration at equilibrium. So for our concentration of the bromine gas, we have 0.063 minus x, where our x here is 0.0178. So once we do the math, we're gonna get the concentration of the bromine gas to be 0.0648 molar. Okay, and then for the bromine atom, we're gonna get Br is equal to 0.012 plus 2x. So our x is the same one, which is negative 0.0178. So once we do the maths, we're gonna get the concentration of bromine atom to be 0.00844 molar. Okay, so both of these are correct because the value are in the positive sign. Okay, so you can also try to substitute this value here inside this equation. So once you try to do and insert that into here, what you're going to get is 0.012 plus 2 negative 0.0105. So once you calculated that, you're going to get your value to be negative 9 times 10 to the power of negative 3 molar. So you get the negative value. So negative value is illogical. Tak logik lah dapat concentration yang negative. So you know that this value is not acceptable. And that is why you need to choose the value of x that is more positive. Okay. So I think that's all for today's video. See you again some other time. Bye.